The gastrocnemius forms the posterior part of the lower leg and forms the bulk of the calf, resulting from the medial and lateral heads of the muscle. It has 3 joint muscles crowning the knee, talocrural, and subtalar joints, and it has 2 heads that runs from the back of the knee to the heel. Along with the soleus, they are the main plantar flexor, or the ankle joint, and are a secondary knee flexor. When running, walking, or jumping, the muscle provides a large amount of propulsive force, and a shortening in this muscle could cause dysfunction with the physiological movements of the hip. The muscle tensions has many fascial connections, which is the connective tissue surrounding and supporting all the muscles, organs, bones, and other tissues in the body, which is transmitted to the foot, knee, hip, and lumbar area.
But how does the gastrocnemius generate an upward force to push off the ground? Well, we can imagine the gastrocnemius as part of a second-class lever system. In this setup, the ball of your foot is the fulcrum. The load is your body weight, centered above the ankle. So it's positioned between the fulcrum and the effort. The effort comes from the gastrocnemius contracting and pulling on the heel through the Achilles tendon. In the second-class lever, the effort is applied farther from the fulcrum than the load, giving us a mechanical advantage greater than 1. This means that the muscle can lift a heavy load, in this case your body, with relatively less force. Mechanical advantage is equal to the effort arm length divided by the load arm length. This lever system is one reason we're able to jump efficiently, even though the gastrocnemius isn't a massive muscle. Next, let's look at torque, the rotational force that helps initiate the jump. Torque is what causes rotation around a joint, in this case, the ankle, and it is calculated as torque equals R times force times sine theta, where R is the distance from the joint to where the tendon inserts, which tends to be about 0.05 meters. The force is F, the force the muscle generates, and theta is the angle between the tendon and the foot, which tends to be nearly 90 degrees. So sine of theta is usually about 1. So if the gastrocnemius exerts a force of around 1,000 newtons, the torque applied to the ankle joint would be 0.05 meters times 1,000 newtons equals 50 newton meters. This torque rotates the foot downward, and that action generates an equal and opposite reaction force from the ground, the force that launches your body upward during the jump. So to summarize, the gastrocnemius leverages a second-class system to maximize efficiency, generates torque to drive ankle rotation, and ultimately allows your body to leave the ground. It's a great example of how anatomy and physics work together to create a jump.
Jump roping originated in the 16th century from indigenous communities and has been practiced all across the world as both a competitive and non-competitive sport. There are competitions for jump rope and often led by the International Jump Rope Union. And the sport can often lead to a lot of health benefits, including cardiovascular benefits, calorie expenditure, and coordination improvement. And it also definitely can strengthen the muscles that it often can come in contact with. It can strengthen the muscles that you need to perform the sport. To explain the physics of jump roping, we'll have to look at the forces enacted upon the jumper and the ground. So the action of jumping up and over a moving rope requires that the jumper fight the pull of gravity. We can apply this to Newton's third law of motion, which states that for every action there is an opposite and equal reaction, or F1 equals negative F2. In this case, the force of the floor is equal but opposite to the force with which the jumper pushes off the floor. So ideally, they're able to oppose with enough force that they can jump over the rope in enough time when the rope is swinging under their feet. Then, once the jumper is airborne, gravity overcomes them and brings them back down to earth. Then they can repeat multiple times. When jump roping, this occurs multiple times per second, which makes the sport a difficult form of cardio and strenuous on the muscle because jumper's body must exert enough force to propel themselves upward at a constant rate. So the stronger a jumper's gastrocnemius, the more efficiently they'll be able to jump up and down. As the large muscle mass allows the jumper to resist the ground's force through contractions and lengthening of the muscle and joints. This diagram can help us see some of the forces enacting upon the person and the forces that the person is enacting. We know that the net force is equal to mass times acceleration. And since there's an equal and opposite reaction, the net force is equal to the force that the ground resists with minus the force of the weight of the person. So that can translate to mass times acceleration equals the reactionary force minus the force of the weight of the person. So then we can derive that acceleration equals the reactionary force minus the force of the weight of the person over mass. And that's shown in this diagram.
Hmm. Well, a jump rope seems like a modern workout tool. It actually goes back thousands of years. Historians believe that in ancient Egypt, children may have used vines or braided plant fibers to jump over. These early jump ropes would have been thick, heavy, and uneven. From a physics standpoint, that means they had a high moment of inertia. Moment of inertia is a measure of how difficult it is to change the rotational speed of an object. The moment of inertia depends not just on the mass and distance from the axis of rotation, but also on the shape of the object. A general formula for moment of inertia is I equals kmr squared, where I is the moment of inertia, m is the mass of the rope, and r is the distance from the axis of rotation. In this case, your wrist or hand. And k is shape dependent, and it's a constant. For example, if the rope is modeled as a thin hoop rotating around its center, then k would be equal to 1. However, if it was more like a rod, then k would be closer to 1/3. Because ancient ropes were heavier and often unbalanced, they had a high moment of inertia, which means they resisted change in motion and took more effort to spin. To rotate these ropes, the hands had to apply torque, or rotational force. Torque is calculated using torque equals R times F times sine theta, where T is torque, R is the lever arm, distance from the axis, F is the applied force, and then theta is the angle between the force and the lever arm. Since the rope is usually pulled nearly perpendicular to the axis of rotation, sine of theta is usually going to be about 1. So the equation would simplify to torque is about equal to R times F. However, rope materials have improved. One example is in medieval Europe when they used a twisted hemp. Because of this, ropes became lighter and more flexible. This lowered the moment of inertia, which meant that less torque was required to spin the jump ropes. In the 1600s, the Dutch introduced double Dutch, where two jump ropes spin in opposite directions. From a physics standpoint, this created a more complex system, where the jumper had to synchronize their motion with the angular velocity of both of the jump ropes, so they had to coordinate with both systems at once. Nowadays, jump ropes are often made from steel or PVC. This makes them a lot lighter and more aerodynamic. In this case, angular momentum becomes even more important. The formula for angular momentum is L equals I omega, where L is the angular momentum and I is the moment of inertia. and omega is angular velocity, which is how fast the rope is spinning. Even though modern ropes have a low I, their high angular velocity allows them to maintain a significant angular momentum. That's why bead ropes can rotate so quickly with such little effort. So whether you're using a vine in ancient Egypt or a modern speed rope, the same physics principles apply, but the materials have a big effect on it.